Okay. Well, this right here was the last theorem we had last time. If R is a ring and I is an ideal inside R, remember that's the analog normal subgroup. And this quotient here is a ring. I already know it's a group because we've had this before. And I just got to tell you how to multiply this. That's the way you multiply. And this function right here, input R, output the coset R plus I, is a ring homomorphism. The first thing I'm going to do is I'm going to prove to you that this is a ring. So I'll give you the proof statement one. Why does this work? Really, the only thing that's of any consequence here is so let me remind you the importance of this. Notice these are cosets, right? You might pick one representative, that coset, right? Because all these cosets have, well, usually have infinitely many things in it, right? You might pick X for your representative. I might pick A for my representative. They both may live in the same coset. We've got to show that no matter what representatives we pick, the outcome is the same. So how do we do this? Well, we'll pick two different representatives. Suppose I pick representative X, you elect A, I pick representative Y. For this coset, you pick B. We got to show that no matter how we multiply it, it comes out the same. So our goal is this. We need to show that when we multiply this way, we get the same answer if we pick different representatives, right? Otherwise, the multiplication doesn't make any sense at all. So let's go back to basics. What does it mean for X plus A equal Y plus A? It means that X minus A is in the coset, or is in I. That's what it means for them to represent the coset, the same coset. And this means Y minus B. Everybody okay with that? So what can I do with this? Well, plus A. Now remember, ideals are vacuum cleaners, right? X minus A is in I, so suck, this is all in I, right? Y minus B is in I, so suck, this is all in I as well. So everybody agree this whole thing is in I? Let's multiply down and see what happens. And notice, of course, my ring's commutative, so I don't care about the order, right? YA and AY are the same thing, so these cancel. Because it's commutative. And so, and I'm going to rewrite it this way, XY minus AB is in I. Because remember, this whole thing was in I, so What does that mean? XY minus AB is an I. That means they both represent the same coset. So my multiplication makes sense. Because this is x plus y, x plus I times y plus I. So that's really, as I promised, that's really the meat of what's going on. That's the heavy lifting right there. Because let's see, what do we got to do? We got to show that this is a ring. Well, guess what? I already know it's a group, right? Because we already know that R mod I is a group. I know that the multiplication makes sense now. And so the only thing left is really to show the distributive property. And actually, I only need to show the distributive property from one side because the ring's commutative. Notice that A plus I times B plus I plus C plus I is equal to A plus I times B plus C plus I. And let's see, my rule says I just multiply these two. And I know that I've got the distributive property of the original ring. So this is AB plus AC plus I, right, which is AB plus I plus AC plus I. So I can break them up like that. And this is A plus I times B plus I. This chunk. And this is A plus I. And so notice it distributes. All right. And that's all we really need. And in fact, notice that since the original ring R is commutative, that means X, Y, and YX are the same. That means that this quotient ring is commutative, right? Because X, Y is the same thing as YX. So X plus I plus Y plus I is Y plus I plus X plus I. And if R has an identity, which I always assume, then R mod I has an identity. Anybody guess what is the coset X plus I that leaves everything alone when you multiply? What's the identity coset, you suppose? Well, that's the additive identity. What are you supposed to multiplicative identity? What can you multiply? So once you see it, it's not so bad. Notice that so this function's like a multiplicative by. Okay. Any questions on that?
What does it mean again to be a coset?
So for example, the coset, we usually did this when we were doing groups, we usually did this multiplication, but I is a subgroup of R, right? If you consider it a group. The coset A plus I is just all the stuff A plus little I as I arranges through all of I. So basically you just translated I by A. So for example, if you have I equals, let's say 3Z. Right, so all the multiples of 3, then that, give me an integer.
7.
Okay, 7. just add 7 to everything and just translates it. Notice that this is the same thing as, notice, in this case, you actually pick the identity, the multiplicative identity for the set. Because notice that 1 is there. This is also 1 plus I. It's also 13 plus I, or any of the representatives. And does that kind of bring it back a little bit?
Thank you.
Okay, I'm going to give you a quick definition that I'm going to need for the next theorem. This is, I think, not too hard to wrap your head around. Definition 1714. When R is reduced, if R has no non-zero, no potent elements. Of course, 0 is always no potent, but if 0 is the only one that's no potent, then we say that the ring is reduced. Let me give you an example or two. The ordinary integers is reduced, and in fact, I can generalize this. Any field, or more generally, any integral domain is reduced. Because in fact, the only, if you don't have any zero divisors, it's impossible to have any nilpotents that are not zero. You can have zero divisors to be reduced. This is reduced. This one, of course, 0 doesn't count in the definition, but the zero divisors here are 2, 3, and 4. They're everything's got a factor of 2 or 3. And you can check that none of these are nilpotent. The powers of 2 flash back between 2 and 4. The powers of 3 are just 3, right? 3, 9, 27, they're all just 3. And the powers of 4 are 4 over and over again. The 8. And Z12, these are not reduced. Because in fact here, every element that is not a unit is in fact nilpotent, right? So it's not reduced. And in Z12, 6 is a nilpotent. That is not zero. So we just say it's reduced if it's got no nilpotents that are into this. This theorem, yes.
Real quick, is 8 bar supposed to be included in?
Yeah, but I really didn't need it because that's the same thing as 0 bar. I got a little carried away, right? Yes, 8 bar is actually 0 bar. Okay. This theorem you might find useful on one of the homework problems. Let R be used. 1 and I are the proper ideal. Number 1, I is maximal. So I'm going to go through this with our kind of ideas that we define. If and only if R mod I is a field. So when you do this quotient structure, it's equivalent. If I is a maximal ideal, if it's as big as possible being a proper ideal, then when you do that R mod I thing, you make that new ring, it's a field. Every non-zero element's invertible. 2, I is prime, if and only if R mod I is an integral domain. That is to say, it's got no zero divisors other than 0. So integral domain, remember we like these because A times B equals 0 means either A or B is 0. And 3, I is radical if and only if R mod I is reduced as per the previous definition. This is actually very useful in pointing out that any maximal ideal is prime and any prime ideal is radical. I think it helps to understand what's going on with this R mod crap. If we look at this. Let's look at the first statement. Let's assume first that suppose well, actually, you know what? Before I look at the first statement, let me it'll probably be better to do this. Let me introduce some notation. Here, I've introduced the notation for sums of ideals before. But let me do this notation here. If I is an ideal and X is in R, this notation is the smallest ideal that contains new element X. So let me draw you a picture of this, and then I'll make it a little bit more formal. If you've got a ring R and you've got this ideal, this little subgroup, it's a vacuum cleaner sucking everything in. If you have some X outside of it, what this is this is the smallest ideal that contains all of this and this. Notice that in some cases, this could blow up to be the whole ring. Right? It could be the whole ring, but maybe it's smaller. In many cases, it's smaller, right? And it's very easy to understand what this is. IX is actually the set of everything of the form alpha plus RX. Where alpha is in I and R is in R. And notice that if you add two things of this form, I'm not going to go through the whole rigmarole here. What happens if you add two things that are in here? This is alpha 1 plus alpha 2 plus R1 plus R2 X. So it's still in there because the alpha 1 plus alpha 2 part is still an I, right? Because I is an ideal, so it's still in there. And notice that the second piece is still a multiple of X. Everybody agree with that? And why does it suck? Because that's what you also need that for an ideal. It needs to suck everything in. If you look at, let's say, if S is in R and alpha plus RX is in X, then S times alpha plus Rx is alpha S plus SR X. And notice alpha S is still an I because the I sucks it in. So that's still an I. And this is still a multiple of X. So this thing is an ideal. I'm going to use this a number of times in demonstrating this. So for statement 1, let's suppose I is maximal. Suppose I is maximal ideal. Now let's look at this theorem here. Our burden is to show that this R mod I, this crazy ring right here, is a field. So what we need to do is we need to show that every non-zero element of R mod I is a unit. That's what we need to do to show that something's a field. You need to take all the non-zero elements and show that you can invert it. They're all units. Everybody okay? Well, so let's do that. Take a non-zero element of R mod I. What does it look like? It looks like X plus I, and I'm assuming it's not zero, the zero element. And of course, this is equivalent to saying that X is not an I. X plus I is not 0 plus I, it's equivalent to saying that X is not an I. Everybody okay? So far. Now, let me ask you guys this. What do we know? We got I, we got this X that's not an I. Let's look at this ideal here. The smallest ideal that contains I and X. What do you know about the relationship between I and IX? That is correct. I mean, for gosh sakes, this thing contains all of I, right? But I'm going to go a step further. I'm going to say it's honest to goodness, really bigger. Can somebody tell me why it has to be honest to goodness, really bigger? That is correct, because X lives here, but it doesn't live here. And what else do we know about I? It was maximal. And so if that's honest to God bigger, then what's true about it? Well, I is maximal, and this guy is bigger. So what's got to be true about this?
What does it mean to be maximal again, that it doesn't?
It means it's a proper ideal, and you can't make a bigger proper ideal. So here we've made a bigger ideal, but you can't make a bigger proper ideal. So what must be true about this? It's not proper, right? And so that means this is all of R. Grows up to the whole thing. Everybody okay with that? Now, I don't know much, but I do know that R contains 1, right? Because this was commutative ring of identity. So that means 1 lives somewhere in IX, right? Okay, so let me translate that into something that I can use. So there exists alpha in I and R in R, such that alpha plus Rx equals 1.
We know that 1 is in IX because it's the identity.
That is correct, and I know that R has an identity, so everybody okay with it? Everybody good so far? Now check this out. So rearranging this just a little bit, Rx minus 1 is negative alpha, which is in I. So when Rx minus 1 is in I, this means that Rx that means that the coset Rx plus I is the same thing as 1 plus I. Everybody agree with me? That was what it means when two cosets to be the same. So Rx plus I is also equal to R plus I times X plus I. And this is equal to 1 plus I. And there you go. X plus I. Because the R plus I is its inverse. So what we've shown so far is if I is a maximal ideal, then R mod I is a field. Any questions? Okay, this was a pick. Pesky both ways, so let's do it the other way. Now let's assume that R mod I is a field. So here we need to show I is maximal. That is, if I strictly contained in another ideal, then all of that. So what I've got going for me is I know that R mod I is a field. I need to show that if there's some ideal in, say, that's bigger than I, then it has to be all of the ring. Well, how are we going to do that? Well, since I is strictly contained in N, let N be an element of I, I'm sorry, an element of N that is not in I. So pick something in N that's not in I, and I can do that because N is bigger than I. Now, consider the coset N plus I, which is not 0 plus I. And of course, the reason that N plus I is not 0 plus I is if N was equal to 0 mod I, then that would mean N is in I, and I picked it outside of I. So it's impossible for this to be 0. Now, the coset N plus I is a non-zero element of a field, so it has an inverse, right? We'll say X plus I. So N plus I times X plus I and let me translate this. This is NX plus I, if I use my definition of multiplication. And so this means that NX well, so for these two cosets, this means NX minus 1 is some element of I. Rearranging this again, this means that alpha plus NX equals 1. Right? So the ideal n contains right, because remember what in is, it's stuff from I plus multiples of n, and that's exactly what this is. So 1 plus I, or I plus n contains 1. Notice that contains n, right? Because everything in I is an n, and little n is an n, and this is equal to all of R. So n is equal to R. Therefore, I is maximal. Any questions? Okay, let's go through this one. I think it'll kind of help augment things. 2. Suppose I is prime. Remember what this means, AB is an I implies A is an I or B is an I. Just a reminder of what that means. We want to show, we need to show R mod I is a integral domain. That is A plus I, B plus I, equals 0 plus I. That's what we need to do. We need to show. Now remember, what's an integral domain? It's a commutative ring with identity first and foremost, but we know that since R is commutative with identity, so is R mod I. So the only thing left to show is that there's no non-zero zero. So we need to show that our little dream comes true. The product of two things being 0 means one of the two things has to be 0. Okay, well, let's freaking go for it. All right, suppose that the product of two things in R mod I gives you the 0 roll. Right? Now notice that I can write this as AB plus I. And what does this equality tell you? AB is in I. Right? For AB plus I to be 0 plus I, that means that AB has to live in I. But what do we know about I? We know it's prime. And the product of two things living in I means one of them has to live in I. Since I is prime, A is in I or B is in I. So translate that. A plus I equals 0 plus I or B plus I, 0 plus I. And we're done that part. So it's an integral domain. So one of the two has to be seen. Now let's suppose R mod I is an integral domain. And we need to show that I is prime. suppose A, B, is an I, we need to show that either A or B is an I. If AB is an I, then AB plus I is 0 plus I, which you can decompose this as A plus I plus B plus I. And since R my I is domain, this means that A plus I is equal to 0 plus I, or B plus I equals 0 plus I. And of course, this is equivalent to saying A is an I or B. So I.
But how do we know that? Like, how did you go from since R over I is a domain, then A plus I plus 0 plus I, or B plus I plus 0 plus I?
Right, because the product of these two things is the 0 element,
Oh, okay,
right? So one of these two has to be 0.
okay. That makes sense. Thank you.
Sure. Okay, I'm not gonna prove the third one. Actually, I did prove it in the notes, but I challenge you to kind of go through it. It's almost exactly the same, except now you're working with radical, which is a little looser than prime. The proof of the third one is short. Look through the notes, and if you have trouble with it, just give me a holler. Now that I've got these preliminaries, what I'm gonna do is I'm gonna tell you about a direct product of rings, which is probably no big surprise to any of you because we already have like the direct product of we've already had the direct product of groups, and this is the obvious generalization. And I'm going to use that for the Chinese remainder theorem from our second point. Definition. Suppose I have a collection of rings. And although I can make this theorem in more general statement, we can just assume that all these rings, as before, are commutative rings about. Because that's what we're going to care about now. We define the direct product of this family of rings. Product of these rings can be a abelian group R1 cross R2 cross and remember what this is this is sort of like a vector. R1, R2, Rn with Ri and Ri. Remember, we've already defined what it means to be a group, and we add things coordinate wise, right? So R1, R2, dot, 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 Rn plus R1 prime, R2 prime, dot, 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 Rn prime is this new n-tuple R1 plus R1 prime, comma, R2 plus R2 prime, comma, all the way to Rn plus Rn prime, right? So just like with the quotient group, I've already got the group part licked. This is a big abelian group. And I am going to define multiplication. I've got to tell you how to define multiplication in direct product. We have multiplication given by R1, R2, Rn times R1 prime, R2 prime, Rn prime. Well, guess what? I need a new n tuple, right? I need something with n entries. What's the easiest thing you can think of to put in the first entry that is something in R1? What's the easiest way you could multiply? One. Well, I can't argue that that's certainly easy. I would agree with that. However, I want something that kind of depends a little bit on whatever the R. So I need a first coordinate here, right? And that first coordinate needs to live in the first ring, R1. And I've got data R1 and R1 prime. What's the easiest thing to do?
R1 plus
Well, that's how we would add, how to multiply.
R1 times one.
There you go. So this is the way that we give the direct product component wise. So for example, let me give a quick example of a direct product before we move on. I put stars and hats so that we don't get our ones, the ones that come out of Z2 and the ones that come out of Z3 confused. What's the direct product? How many elements would this direct product have? Huh? Well, remember, what you have is complete freedom. These are two vectors. You got two choices for your first coordinate. You got three for your second.
Six.
I agree. In fact, 6 is small enough where I'll list them. And for example, how would you multiply things? Well, 1 bar times 2 star times well, this would be 0 bar and 1 star. By itself should be 1 bar and star. Just multiply the component lines. By the way, what's the identity? What's the multiplicative identity? That is correct. And in fact, you can generalize what he said to this. What's the identity of the direct product? Just put a 1 in every coordinate, right? And that's it. By the way, what's the additive order of this? How many times you got to add this to itself and you get back to the identity? When you add this to itself, what do you get? 0 bar, 2 star. Correct? Add it again, and I'm back to 1 bar here, and I've got 3 star here, which is 0 star. Agreed? Add it again, and I get 0 bar, 1 star. add it again, and I get 1 bar, 2 star, and I add it, finally, I get 0 bar, 0 star. So the order of this element is 6, and notice how it orbits through all the elements of this.
Is that just a coincidence that it's the same? But like, in this case, it had to go through all elements?
It is not a coincidence. In fact, because 2 and 3 are relatively prime, and we're going to see this from the Chinese remainder theorem. Anybody want to guess what's a more convenient way to write this? You've seen this before we did direct products. You've actually seen this ring. You've seen it in different sort of guise. This is Z6. This would go 1 bar, 2 bar, 3 bar, 4 bar, 5 bar, 6 bar, which is 0 bar. And in fact, if you do that correspondence, if you take the function that assigns the orange number to that, that will give you an isomorphism, a ring, a 1-to-1 and onto ring homomorphism from Z6 to Z2, Z3. Yes.
So any other, any other 2 products together?
I am going to give you another point of view on the Chinese remainder theorem, and I think it may answer your question. Because yes, you can, so for example, when it give me 2 relatively prime numbers, say 15 and 16. If you take Z15, direct product Z16, 15 times 16 is what, 240? That's actually isomorphic to Z240. That only works because they're relatively prime, but you have to be careful if there's an overlap factors. And we will talk about that presently. Let me give you a definition that we're going to need for next time. Definition. See, I thought I found those up there. Let I and J be ideals. And I want to be proper. The ideals I and J. I plus J, which does not have to be proper. Is a set of elements in form this way, alpha and I, beta and J. I plus J is, I think, what you think it is. See if you can prove for yourself that this is an ideal. We say I and J are co-maximal if I plus J all of R. Okay. Any questions? I am going to give you a more general statement of the Chinese remainder theorem and hopefully finish that up next time. But I will leave you, since we were kind of waning on time a little bit. I'm gonna, this is a corollary. Next time, you say Chinese remainder theorem from ring point of view. Right, we've already stated the Chinese remainder theorem initially from modulo arithmetic, right? Systems of equations. We'll say from ring theory. point of view, and it will give the following corollary. If GCD of AB is 1, then C mod A cross C mod B is isomorphic to Z AB. And so more conveniently, sometimes you might want to do this. If N equals P1A1, PKAK, with PIs are distinct primes, and each AI is greater than or equal to 1, this is isomorphic to Z P1A1, Z P2A2, the Chinese remainder theorem allows us to break up Zn as isomorphic to a direct product of Z mod its prime powers. This easily allows us to do things like compute units, zero divisors, nilpotents, things like this. And we will explore this next time. We'll finish up a little bit with finite fields, certainly by the end of the week. And then we're going to do some coding. We'll send some messages, figure out a little bit of RSA, and do some Rubik's Cube stuff. Any questions? Yes, sir.
Or like ideals, when you say that they suck, it's only when you multiply them, something that they put into the ideal.
Yeah, what I mean by they suck is if you have any element of the ideal, whatever it is, and you multiply it by an element of the ring, it's pulled into the ideal, right? So if A is in the ideal, R is in the ring, R times A is in that ideal. Other questions?
You made a statement before, like the identity of the direct product. You said that there has to be one in every element.
Mhm.
What exactly does that mean?
So suppose I have R1. And suppose each of these rings has identity. Notice if you have your typical element here, say X1, X2, Xn, where these are all elements, this is from R1s, from R2s. If you multiply this by or this is the one element in R1, this is one element in R2, and so forth and so on, you get the same thing, don't you?
And when you say the one element, like literally just the number one. or the
Well,
identity?
So for example, if this were a matrix ring, the one element might be, you know, an identity matrix, which
Okay.
isn't really the one
So it's the identity
of each separate ring.
of, okay,
Right, exactly. So here's another silly example. If I give you the ring 0, 3, just consisting of those two, and my addition and multiplication is mod 6, that means that 3 plus 3 is 0, means 3 times 3 is 3. Notice that this is an identity here, because 3 times 3 is 3, 3 times 0 is 0, and so forth. But it's not really a 1, right? So your identities are these different, these are separate rings, so that they might have different identities. Others? Okay, y'all have a good one, and we will see you next time.